As with all of this, it's not a complete guide on everything about bin picking, but we're going to touch on a lot of the elements that go into bin picking, at least the major things to keep in mind as you decide that you need to pick parts out of a bin for the robot. Okay? So this is going to be how to succeed, an overview of part presentation in general. There will be a much more involved part presentation tomorrow by Brad Chekalinsky, I think. He's got a lot of experience with things like the any feeder that you see there, all the different options of presenting parts to a robot. We're going to overview a lot of them. We're going to touch on a lot of those, but at a very surface level kind of examination. So without further ado, like I said, part presentation, we're going to talk about what is bin picking. Pretty much exactly what it sounds like. What are the considerations for 3D bin picking that come up and that are really important to keep in mind? And what solutions are actually out there? And then there's a live demo behind you guys for those that are interested. Presenting your parts. Kind of make this interesting somehow, right? The transitions. You don't need to pay too much attention to these radar graphs. Basically what it is, the more shaded it is, the better it is typically in that area, okay? So we have expertise needed. Farther out means it's super easy to implement, not a whole lot of training needed. Ease of use means how easy is it to actually deploy once you know how to use the system. Initial investment, the upfront cost, and the capability of the system, right? Meaning either how much error can it handle, what kind of parts can it handle, what kind of surface finishes, geometries, all that kind of stuff. How capable is your system, right? The key takeaway from this slide, without going into too much detail, on one side you have mechanical singulation that is very intuitive, can be very easy to implement, and the initial investment tends to be pretty low. If you're talking about mechanical singulation means jigs or fixtures or things like that, right? Random bin picking, as you get closer to this way of picking parts gives you the most flexibility by far, right? Because what could be easier in terms of presenting a part to the robot than just dumping a bunch of it, or dumping a bunch of them into a bin, and just letting a camera figure out how to tell the robot to pick it up, right? Once you get to that point, it's extremely flexible, but the barriers to entry for bin picking are much higher. That's the trade-off, right? So there's a spike in one area, all the other areas tend to be harder, right? So that's the key takeaway from this slide. Mechanical part singulation, it can be the cheapest and most straightforward if A, your parts, and B, your process allow it, okay? So nests or trays, pretty easy. If you tell someone, nest these in a tray, pretty much everyone knows what that is without ever actually doing it before, right? All you need to do is have some sort of routed out tray that holds your parts in a specific location and orientation. Conveyor guides, as you see here, you have parts scattered along a conveyor, but you can use guides to push exactly one out at certain intervals. So a robot only needs to go to this one spot. The orientation is more or less, it's at least mostly constrained, right? Like the can rotate, but in general, a person can blindly sit there at the end of the conveyor, move their hand to this exact spot, and pick up a can on a certain interval. So you can use conveyor guides. Ball feeders are a little more involved, but it's kind of these tend to be very customized solutions, but they're still, I'm calling it mechanical. This is kind of the same concept as a conveyor, except that your parts, you just dump them in a bowl, and you use mechanical fixturing and vibration to push them along a track. Not push them, if you ever see it, it looks kind of like magic. There's a lot of tweaking and custom fixturing involved to rotate, to either filter, rotate, orient, or all three of those for your parts. But at the end of the day, what this is parts in a bin turn into parts coming out at a specific location for the robot every time, right? This requires that you go upstream from your robot process and figure out how to actually stage your parts, right? So the slight trade-off there, it's super simple, but you need to handle the part and do some work to make the parts consistently presented to the robot. But if you need to deploy your solution very quickly, and you need it to cost as little as possible, mechanical singulation might be the best path forward. Make sense? Good on mechanical singulation? Again, this is just a brief overview. This is by no means the last word on any of this. 2D machine vision, now your barrier entry has gone up a little bit. Your location is mostly constrained. Your orientation's not fixed, but it's mostly predictable. If you have this super complex part that can lay on a table in a bunch of different orientations, 2D vision is probably not the way to go. The example you see here is cylinders, right? What this means is he doesn't need to nest the parts. So you guys, I don't know if you guys recognize this picture, but this is from that Walt machine example, right? Where his throughput demand went up because he landed this huge order for camera housings, and he didn't have the capacity, so he implemented a robot or a cobot to do it for him. Because this is running overnight, he can't sit there and nest every single batch of parts that are presented to the robot, right? So he's using 2D machine vision. He knows these are flat cylinders. They can only lay on a table one of two ways. And honestly, because it's a blank cylinder, it doesn't matter which of those two ways it is. It's basically the same. So you can use a 2D camera to tell the robot where the part is on the table, and then the pick process is, the approach is basically exactly the same every time. 2D vision's great for that, okay? Some options can be easier than others. So Robotic makes a wrist camera, you mount it directly to the end of your UR, you program it from the pendant, super easy to implement. Lots of options are out there. That's probably the easiest to implement solution I can think of. And then we move to 3D, yes? Train what? So 2D machine vision in this case tends to be, now I'll let any of our technical guys jump in, or we can catch up after the presentation. 2D machine vision, when you're picking with a robot, most of the time what it's doing is just, you've trained it what to look for, and then it finds the best match out of what's in front of it. So it just finds the best match and tells the robot to go to it. I'm not saying you can't do what you're saying. It adds complexity to your programming, and there's a lot more thought in it. So in this case, we're just talking about locating a part, moving the robot to it. So 3D machine vision, now we've gone up another step in complexity. It can be, really there's three subsets to this 3D part picking, right? There's structure, so you still stage the parts, kind of like in 2D, but now you're really picking it out of maybe multiple layers where the exact layer arrangement's not predictable. Actually, structure is, it's every layer's the same, it's just now you're doing it in 3 dimensions. So you have a much higher depth of field than just on a surface, right? Semi-structured is kind of like this. Like they tend to be kind of you make sure that your parts are maybe oriented roughly the same way, but it's still not just dumping them in a bin. And it's not staging every single part. In 3D, these are typically the most complex vision systems that you're going to find in machine or vision-assisted robotics, right? I explained structured and semi-structured. Both of these, kind of like mechanical part simulation, they require that you handle your parts upstream of your picking process, right? So there is work. The trade-off for simplifying the 3D machine part of it, or the 3D vision part of it, is that you have to touch your process upstream and maybe overhaul it a little bit. But if you're successful in doing that, it can simplify your 3D vision requirements by a great deal. So that's all good. If you absolutely can't do that and your current process is the parts are being dumped into a bin, I see this a lot in injection molding, right? Parts, a big gantry robot grabs the parts from the mold, but then it just kind of drops them onto a conveyor, and then that conveyor empties into a bin. That's pretty common. It doesn't have to be a bin, it could be in a pile or a pallet directly on the end. But either way, that's a lot of work to overhaul that to nest all your parts. You have to basically retool the entire process, right? So If you can't do any of that upstream staging, then we're left with random bin picking, right? And I say the holy grail of part pickup because this has been one of the most difficult things to reliably automate. There's a ton of solutions out there, but it's been hard to get a process completely robust historically, right? So random bin picking is exactly what it sounds like. I've given you kind of what the camera sees in a bin right there, identifying parts, but it's parts in a bin and you don't have any staging for location or orientation, right? Do you guys have parts in bins at your facilities? So you're just dumping parts in, operator moves the bin to the next part, and then someone's picking parts out of a bin and doing something else? It's pretty common. And it's the simplest way to move parts without having to stage each part, right? This is something that's really simple for people to do, right? So even if you have something more complicated than washers, right? Say you have little toy horses in a bin, any one of you guys could probably blindfold yourselves, reach into a bin, pick up one horse, and then set it right side up on a table. We just know how to do that. It's actually so easy for us. If you had to explain to someone every step that you were doing in your mind automatically, that's harder than actually just doing it, right? But when you're automating it, that's what you have to do. You have to account for everything that's actually going on at every step of the process. How do you know where the bin is? Well, first with your eyes, you find the edge of the bin. Then you put your arm out a certain way so that you don't hit the side of the bin. All these little steps get pretty hard when you try to automate it. Random bin picking, generally the most expensive and trickiest option for part pickup with a robot. That probably goes without saying at this point in this presentation, right? But it's basically what we do with our eyes. They see the contents of the bin and they pick the best part for the robot to go grab. Any questions so far? Sweet. So part of a bin picking solution is the camera itself. We'll get into what camera technologies there are, but the software is kind of what drives all of this, right? So the software, what it's doing with every cycle is, like I mentioned, it determines the best part to pick up based on the percent match, or it identifies individual parts based on the percent match with your top model. Usually you teach it with a CAD file, or there's some systems that you can teach it kind of on the fly by presenting it a bin of parts, and you tell it this is what a part looks like. So it bases this percent match for the best pickup candidate with comparing it against the model. Is the part obstructed by other parts in the bin, right? So that's something we don't think about, but we automatically just account for it when we're picking up parts, right? If you have parts stacked on top of each other, the lower one is not as good of a match to pick up as the top one, right? So that's one of the factors. The location in the bin, if it's way jammed down in the corner versus you have one kind of towards the middle of a bin, think about like the last couple of parts in a bin, right? One out in the open towards the middle of the bin is going to be better than one sitting in a corner, right? So location in the bin. How can you approach the part without for example, if you have a gripper on the end of your robot, how can you approach the part without the gripper hitting the bin and causing a collision, right? So that's another thing that the software calculates. After the software does that, it tells the robot, all right, these are all your offsets, you're gonna execute your approach path with this offset applied. And the robot goes and executes that. Now the software, it's pretty likely that you'll be able to pick up a part in multiple orientations, right? Like with my toy horse example, you can pick it up upside down out of the bin as long as you have a way to reorient it and put it on the table. Maybe you'll put it on the table, that could be a position that you teach to the robot, and when you execute that pick in your program, you just say, okay, I'm gonna take it to a station over here, set it down, and then regrip it. After you leave the bin, everything you can control, once you have the part in the robot's hand, right? So the software will get you all the way up to the pick process, and then you can reorient the part or whatever based on your process. This is a simple diagram of a bin picking system. everything in the square represents what the hardware and the software is doing, mostly software, right? So it's randomly piling parts, picking one, it's doing part detection off the camera somewhere on a separate processor. CAD model fitting, all that stuff is being done by the software, and then it communicates all that to the robot controller, which guides the arm. I can send any of you guys a picture of this, by the way, if you want a bigger version of this, so you don't have to take a picture of part of the slide. So what do we consider when we're actually looking at a bin picking application? Well, number one is going to be your part geometry, right? If you have springs and coils, it's highly unlikely that you're going to be picking exactly one of them out of the bin. Even if you can detect them and tell the robot where to go, you're probably going to grab more than one part every time. So if your parts entangle easily, it's not really a good candidate for even semi-structured bin picking. Complex features, I'm not going to say this is impossible, because our system back there can detect a huge variety of parts and complex parts, but in general, the simpler your part, the less time you're going to spend programming the system, and your deployment time shrinks. So this washer, there's only two ways it can sit. There's only two stable orientations of it, right? A good test for this is if you take your part and you put it on an empty table, how many different ways can it sit on that table? The less ways there are, the less complex it will be for bin picking. So this jack, not only does it have these small intricate features, but it could lay all sorts of ways. And it could probably get entangled in the bin too. So super complex parts, the simpler the better, basically. Especially small features, like that jack looks pretty big on the screen, but like a little jack, most camera systems don't have the resolution to pick up that level of detail with as much detail as you need to pick it up with a robot. Symmetric parts are easier. Part thickness, most of the systems on the market don't do great with super flat parts, right? So if you have thin sheet metal parts like that, the part itself is just not thick enough for the camera to read an accurate depth measurement. So under 3 millimeters tends to be kind of a no-go zone for a lot of systems. At the very least, you're going to need to investigate it a lot further and do a lot of testing. And then the surface finish, matte surfaces are always going to be easier to work with, no matter what system you have, right? Shiny and translucent surfaces, they reflect light, they diffuse. If you have a laser sensor, they'll diffuse that laser. They tend to be pretty problematic. So I said laser, so let's start off with that one. Basically, anyone ever use a laser distance meter? So like you point a laser pointer at something and it tells you how far away you are. I think that times about 1,000, and that's in a nutshell how this laser system works. It scans a pattern with the laser and determines how far away each point in that pattern was and compiles kind of like a surface map, whatever it scanned. Structured light, similar concept, but almost entirely different. So we'll just say it's a different technology. Structured light means, on one hand, you have a projector, you have a known pattern, right? And you shine it onto a surface. And then with a camera, you look at all the deformations in your pattern. I forgot to advance this. So that's a laser scan going on, right? So a laser, you can do profile scanning, so scan just in a line. So imagine if you have, let's say, tubes in a bin just as wide as the tube, right? Or a cord of firewood. You don't need to do a full 3D image of the entire top of it. You just need to scan in a line along the middle, and then you can see which piece of firewood or whatever is the best one to pick. That's something that you could do with laser line scanning, or you can do a 2D inspection by scanning that line over an area. Structured light, so the structured light projector projects that known pattern, right? And depending on the shape of the object that you're projecting it on, it's going to deform the pattern in different ways. So your camera sensor picks up the reflected pattern, and then all your software, your computer does a bunch of math Think of it as a black box that basically decodes that pattern and interprets the depth of everything that it's looking at, right? And then there's stereo vision. A stereo vision sensor is obviously not human eyes, but it works on the same principle as why we have two eyes, right? So you have one image here, you have another image here, you compare the two, and then you can kind of correlate the depth based on the differences between those pictures, right? Stereo vision tends to be very heavy on the software side. How robust a stereo vision system is heavily dependent on the software driving it. So that's a brief overview of the technologies. The next thing is, beyond your sensor and your parts and everything, is your actual bin, right? So this is kind of an interactive portion, because those are always fun. On a scale of 1 to 3, right, if you had to rank these three options, where do you think this one would fall? 2? Everyone agree? Okay, well, I messed up. I forgot which order I had these showing up in. This one would be the easiest, right? So this one would be 1. Whoever was thinking that already, congrats. Why is this number 1? Well, you see it has more or less straight sides, right? There's not a lot of geometry inside the bin, so it's all smooth. Simple geometry on your bin means less things. The part can get caught in less places, right? So you don't have to worry about any of your parts getting caught on bin geometry here. You also have very predictable robot paths, right? And straight sides means the shape of all your parts as they sit in the bin is also pretty predictable, right? You guys were right, this is number 2. It's not so bad because it's still got straight sides, but it's got all these little crevices in here that can present problems later on. Most bin picking systems don't really care about the inside of your bin, they just care where that outside boundary is. So having super complicated features on the inside of your bin can lead to unpredictable situations with your robot, right? And then who wants to tell me why this one would be a nightmare? Okay. Sloped sides. It's steep, so it's a deep bin. And the key thing here is it's clear. Not so much the body of the bin, but the camera is going to have a much harder time looking at the opening of the bin if it's clear and not opaque, right? So those are some of the things to look out for in a bin. We'll talk about how to deal with that. There's basically one key point that solves a lot of this, okay? Top bed should be opaque. This probably goes without saying, but the bin needs to be placed. You do have to stage the bin itself to some degree, right? And that's probably obvious, but it needs to be within the camera's field of view. And Effector Design. My confidence has been shattered in the order of the smiley faces, so we'll just step through. Yeah, that's good. I never would have gotten that. Why does this one get the red sad face? Yep, that's exactly right. So this end effector is complicated, right? You can teach it. So you can upload a CAD model of your end effector and the software will figure out how to approach your part so that the end effector doesn't collide. But the more complicated your end effector, the more time that calculation is going to take, right? So you can expect your cycle time to go up if you have a crazy end effector. This one's a little better. The chances for collision, so this one's just one simple gripper, right? But it flares out with the fingers. So the chances of there being a collision issue or not being able to grab a part with this because it's tucked away in a corner tend to increase with something like this. So this one's the worst. I won't say worst. Out of these three, this one would be the toughest to implement. Followed by this one's kind of mid-range. The ideal situation is, if you can help it, is one vacuum cup on a shaft of some kind. That gives you the best approachability to your parts, the least collisions with your bin, just gives you the quickest implementations in general. This is one that we designed, and all things considered, it does have this one fitting, which limits sometimes how it can approach the bin, because we did have this catching on the bin at first. But all things considered, this was pretty easy to implement, because it's mostly a cylinder with a cup on the end. Much easier to reach into a bin with just a stick than, I guess, one of those pickup assistance things, right? One key thing here, one thing that makes it a lot easier to do bin picking for your end effector is to make sure that your end effector can reach the bottom of the bin without your robot arm needing to go into the bin. Does that make sense? That way your robot arm doesn't hit the bin and drag it off the table or whatever on its way back out of the bin or during the approach, right? So these, like I said, these are for finding a part and then communicating offsets to a robot. There's not a lot of path planning that goes on, so you're not dynamically telling the robot, I need to move this way into the bin. You're telling it, this is your general approach point. Based on the location of this part, offset it here and go and pick up the part, right? So if you can avoid reaching into the bin with the actual robot, it makes your application a lot simpler. Cycle time considerations, this is going to be affected by a lot of things. There's a lot of tweaking that you can do, but in general, it's going to be affected by your parts geometry, the density, the packing density of your part in the bin, the surface finish, how precise do you need your pickup location to be. So if you say, I've got this part, but I can only pick it up, say you have a small vacuum cup, I can only pick it up exactly in this location. It's going to take a longer time to find a perfect match for that, right? It's going to need to do a lot more computation in the background. So large, simple parts with a matte finish, multiple possible pick points, and simple geometry are going to decrease your cycle times. Does that make sense? Why? So this part you have a lot of, like the toy horse, you can pick it up right side up, left ways, whatever. You have a lot of flexibility in picking it up, so you don't need to do as much calculation. Which one of these do you think would be easier? Right, because that would be a nightmare if you had a bin full of those and a machine camera, right? Cool. Deployment time. So, in our experience, there are going to be situations, once you're in the middle of a bin picking application and you're deploying it, there will be situations that you didn't think of, right? Because this is so dynamic. The lack of structure in staging your parts means there's almost unlimited variability in what the camera is going to come up with, what the computer or the software is going to calculate, how the robot is going to interpret commands. So many different situations can happen. So it's critical to leave enough time for testing so you can run through a large number of repetitions, basically, to allow these different situations to play out. A lot of things can drive this part orientation. The parts could find themselves oriented in a way that you didn't predict. Normally what we think of when I say unpredictable situations is collisions, but there could be situations where you have all your parts in the bin, nothing looks like it's unpickable, but the camera doesn't find a match because something very subtle is happening there that's different, that you didn't predict, right? So this will happen just because the bin picking is so unstructured. So you need to leave a lot of time for scenarios, all the different scenarios to play out to make a more robust process. So what's out there? Pickit 3D, some of you guys might have heard of this, especially if you've been looking into the URs. This is a structured light sensor. You can teach it apart without any CAD. It's got some different learning engines in it. You can mount it on the robot wrist or stationary, like we have that unit mounted there. Their focus is on the ease of use. Okay, so remember how I talked about the different areas with the sensor? Their focus is ease of use, so that you can program it from like a web-based environment. Their minimum cycle time is 3 seconds. So if your process requires faster cycle times than that, Pickit might not be the best solution, right? They have a minimum part size of 30 by 30 by 30. I think they just came out with another model that reduces that slightly to 5 millimeters or so. The repeatability is 1 millimeters to 10 millimeters, depending on which model you get. Unfortunately, it's not super great for flat parts or translucent parts or reflective parts, right? Which isn't a dig on them, it's just those parts are hard to automate, right? And their focus is ease of use. If you've got soda cans in a bin or something, this may be a more appropriate system. The scanning ruler, the nice thing about, so this is a laser-based system, the nice thing about laser systems is that they're immune to ambient light. So it doesn't matter if you put it under a skylight or what type of lighting you have or if your lighting changes, the laser doesn't care, it's just the distance measurement, right? You can typically have pretty large fields of view because you've got these little mechanisms moving that laser line around, so that gives you a larger field of view than a static camera, right? It's got a pretty decent working distance as well. So the cycle time is a little better, 2.5 seconds. I could not find a spec on the minimum part size. I'm sure there is one if you delve deeper into evaluating an application. The accuracy is 1 to 4 millimeters. This is good for flat parts, right? Translucent parts and reflective parts cause more problems because they diffuse the laser and throw off readings. And what we found to be kind of the Ferrari or the Cadillac, if that's your type of car, of the machine vision offerings is the RV series from Canon. This has the most robust part detection of anything. So it can handle flat, translucent, and reflective parts. It's been able to handle whatever we've thrown at it so far. This is externally mounted. If you look back there, that camera unit's kind of hard to put on a robot. However, there are slides if you need to move the camera around. There are options where you can mount it on a linear slide and it controls that whole system as one. It can do, so if you have different parts in different bins that are kind of in the same area, it is capable of handling like kitting applications. So you pick one part from this bin, one part from this bin, all with one camera. And there's a dictionary option. So that's kind of hard to explain. The best way I've been able to do it is with a analogy. Okay, so you guys have fastener, those boards that you have up near where all your bins of screws and things are, they've got a bunch of female threads, a bunch of male threads. So if you have a screw that you pick up off the floor, you could take out your calipers and measure the diameter and the pitch and the length of the screw, the head size maybe, and calculate what the size of that screw is. Or a quicker way to do it, if you have one of those fastener checking boards, is to just go try each one and then see which one fits. Oh, that's an M4, right? Dictionary option is kind of the same thing. It stores all the orientations of your part in CAD and your point cloud. If you go back there, the Canon guys can probably give you a better overview, but instead of calculating the match of a part, it just runs a comparison to a database, and that speeds up the cycle times, just like checking the size of your fastener with a board. So that's kind of probably a pretty non-technically savvy description of the dictionary option. But that is something that greatly speeds up recognition times for complicated parts. So as a bird's eye view, we're good. In general, lower cost versus capability versus ease of use, you can pick two of them with most systems, right? If you have complicated parts that aren't appropriate for other systems, check out Canon. Their system can probably handle it. With any of these, one of the big red flags is if anyone says, our system can handle your part no problem without testing. The first step you should do, if you're looking at a bin picking system, is plan on having your parts tested. So, two good reasons for that. One is a sanity check that a system is appropriate for your parts. Two is you save a little bit of time by having that step prepared. Hey, we're ready to send you sample parts, right? So finding the best option involves testing, like I just said. Knowing your parts, kind of knowing the materials, what can be changed upstream, what can be changed in your process. Knowing your actual process and your constraints. Can you stage the parts, or do they have to be in a bin, and why, right? More testing. Know your environment. What are your lighting conditions like? What are your cycle times? What are your floor plans? Cameras typically have a working distance, right? Which means you can't put a bin of parts right here. on a camera and look at it this close. You're only going to see this much of it, right? So cameras are going to have some sort of optimal working distance. So if you have enough overhead space where you want to put the system to raise up the camera and mount it up above. All things to know about your environment, and then testing, both when you're evaluating a system and when you're deploying it. Like I said, leave room for a ton of cycles. Key takeaways, I'm sure you guys have put this together in your heads so far, but bin picking should be used because it adds complexity and cost to a robot deployment. When you can't change your upstream parts or processes, upstream processes, bin picking starts to be a more justifiable solution, okay? Know your parts and processes. This never hurts. Leave time for troubleshooting and debug. Unpredictable things can and will happen when you're testing out a bin picking system. The simpler your process, the simpler your parts, the simpler your system in general, the quicker you're going to be able to get it up and running, okay? And don't commit to anything without testing your parts. Vision can be a very tricky thing, right? It's not like mechanical grippers where you can sketch some numbers on a piece of paper and determine, okay, this is the gripper width I need, this is the finger geometry I need. Vision can be very tricky and unpredictable. So testing your parts is a critical step in implementing any bin picking solution. So, with that, thank you. We can do, by the way, we can do parts evaluations for bin picking. So if your ears have been perking up this whole time, come see me after. We'll figure out how to run a test. Thank you guys.